Hello, everyone. Thank you for giving me the opportunity to present our work titled Deep Hierarchical Reinforcement Agents for Automatic Penetration Testing. This work is a result of a collaboration between the University of Technology, Sydney and the Defence Science and Technology Group in Australia. This is the outline of my presentation. I'm going to start by defining the problem, giving an introduction to automatic penetration testing application and its challenges. Then I'm going to move on to explain the methodology, which is using deep reinforcement learning to address the challenges of automatic pen testing. At the end, we're going to give you a few experimental results on our current work so far, as well as some insights we have from developing this work. Automatic penetration testing is to simulate an organized attack strategy from a red agent or the attacker perspective to compromise network systems. This is a time-consuming process and requires a lot of human resources, such as time, expert knowledge, and skill set in order to perform. It is desirable to have an AI or artificial intelligence-based tools to develop strategies for effective penetration tests. There are associated major challenges to this application. For example, high-dimensional state and action space. The size of state and action space can go up to thousands or millions, even with medium-sized network. There is also stochasticity in action policy. For example, within the same state, the same action is not always successfully executed on the networks. This represents the probability of success in real-world application. The environment is also not fully observable to the attacker agent, where a lot of information such as the subnet connection, as well as the connection of hosts within the subnet is hidden from the state vector. The asset or the variable flag is hidden inside of one of the hosts in the network, is completely hidden from the agents. On the right, we see the illustration of an example scenario developed by the Cyber, which is also the simulator developed by the defense group. The red agent here represents the attacker, and it stays outside the network system. In this work, because of the stochasticity and the dynamic of the environment, we cannot use supervised learning to develop an AI agent. In fact, we're going to use reinforcement learning, where it models the interaction between an AI agent and the environment. The agent is rewarded with a positive reward signal if it exercises the right action in certain states or achieves some goals in the environment. In our case, if it is successfully captured a flag or gain access to some host in the network. The reward signal can also be negative if the agent selects the invalid actions. There are different reinforcement learning methods, such as policy-based or value-based or a combination of both, which we call actor and critic. In our work, we use value-based methods called deep Q learning and with the dueling architecture to make use of the experience trajectories and to save up some training time. This will estimate the state action value function Q of S and A in order to learn the best action to take in each state. Current deep reinforcement learning algorithms are not stable in high-dimensional action space. The equations of the Q values are defined in the lower right corner. This is the expected cumulative future rewards as the agent explore and take action in the environment. More formally, we need to define the markup decision process for this application, which is the state space, the information the agent gets when interacting with the environment. The action space contains all the available actions that the agent can exercise on the environment. A probability transition dynamics, which defines the probability distribution of the state given the agent taking certain actions in some states. The reward function is the mapping from the state to a real number scalar to define the kind of output the agent interact with the environment. And then finally, we have the discount factor representing how far ahead the agent take into account the reward signal. The two important equations, which is the V value function, which is the third function here, and the Q value function, which is defining the value of taking certain action in some state. They are both represent the cumulative reward the agent can achieve interacting with the environment. And the goal of reinforcement learning is to maximize this cumulative reward signal. In our work, we decided to perform an algebraic decomposition of the action space. So the size of the action space is denoted as the capital A, with the actions identifiers being from 0 all the way to the size of the action space -1. This is the convention of denoting the actions in reinforcement learning. So because of this, the action space can be extremely large which means the action identifiers can go up into like thousands or millions of values. Our proposal is to algebraically decompose the original action space into groups of smaller values, which we can design RL agents to learn into subgroups. Intuitively, the below illustration demonstrates the meanings of this decomposed scheme. The top level, level 1 agents, outputs an abstraction action identifier, which then traverses down to second level agents. The outputted level value of the agent level 2 was basically shifted to higher values depending on the outputted value of agent in level 1, up to the last level, in which the outputted value of the last level was shifted by all the values of the previous levels. This ends up with scaling the final action identifier to be in the range of the original action space. This decomposition scheme has a main advantage of scaling the action space to be manageable to 20 or 10 to 20 actions per agent, which is our design choice, which is manageable by a conventional deep reinforcement learning agent. The illustration on the right showing a more formal way of combining the actions from agent in level 1 up to agents in level L, which is at the final stage, the A out at the level L is the suitable action that we can exercise in the environment. So in our architecture, all the agents will share the same reward signal from the environment. So as a group, each agent learns the optimal policy on its own to achieve its own maximum future discounted reward. As long as each agent can learn this optimal policy, then the entire group can achieve the global optimal policy. The guarantee of optimality, we're going to discuss that in the later slide. The action space of each agent is significantly smaller in this case than the original action space. As I said earlier, the actions for each agent can just be around 10 to 20 actions per agent, which is our design choice. The number of agents can be roughly calculated as a logarithm of the original action space, as it matches the depth of the tree. So in this case, this is not really a binary tree, but in certain sense, it resembles a binary tree. Furthermore, the training and execution of the agents can be done in parallel, as the illustrations on the right, where all the agents basically share the same replay buffer. The actions in the replay buffer is a joint action of all the L agents in the architecture. And leveraging the deep learning frameworks such as PyTorch, we can perform all these updates of the training and execution in parallel. As a result, the increase in computational complexity is sublinear to the action space increase. Current empirical results are promising compared to the use of just a single agent's performance. This is how we set up the experiment using the cyber developed by the SDG group. We're going to set different scenarios with different numbers of hosts in the environment, and we verify the performance of the proposed method in comparison with a single DQN agents. All the agents network in our examples are implemented using Turing architecture of deep Q-learning. The agent represented by the attacker in these illustrations needs to find a strategy in order to penetrate to these networks and gain access to the flag, to the hidden flag within the private subnet. So in the demonstrated experiment over here, we show you where the two positions of the flags can be. The number of hosts vary from 6 to 100 with the corresponding states and action space number, and the required number of agents we develop for each of the scenarios. This is, to our knowledge, the first time where a deep reinforcement learning architecture is performing on this scale of penetration testing application. We present here the outputs from 4 different scenarios, ranging from 50 hosts up to 100 hosts. So for each of the figure, we have 2 metrics to measure the performance. The first one is the accumulated score during training and the number of required steps to get to the flags. Each experiment was performed 5 times with different randomnesses. Therefore, we have the variance between runs in the plots. So the left figure represents the accumulated scores during the training, and the right panel in each of the plot is the required steps to achieve the target. Of all the tested environments, the HA-DRL or the hierarchical agent performs similarly to or outperform the conventional DRL agents. It can also learn the optimal policy to achieve the highest or the maximum possible accumulated score with quite stable performance. So in all experiments, the performance of HA-DRL have lesser or smaller variance compared to the one from the single dueling DQN agent. In addition to the convergence results, we also perform state clustering using Disney to visualize the state representation learned by the three agents in the hierarchy. This is the three agents we use in the testing of the 50-host scenario. So in this illustration, we explore the state representation learned independently by each agent in the hierarchy and group them by the action they take. This shows us the policy pi of taking an action in certain states. The interesting thing here is that even though the agents do not know the structure of the private subnet, it does represent the states into a number of clusters, which is similar to the number of private subnets defined in the scenario. For example, in here we present a scenario for 50 hosts where we have 9 different private subnets. Additionally, this cluster information can be used to form subgoals for learning in more complex settings, which we are doing at the moment for our ongoing work. So this is our insights when working on this project. The current results encourage further research in developing hierarchical agents in handling complexity in states and action space of automatic penetration testing applications. HA-DRL, as we call it, as a structure can be implemented with any other reinforcement learning algorithms. At the moment, we only verify this on DQN algorithms, but there's no constraint on using other methods. The agents in HA-DRL follows independent training and execution, which is known in the multi-agent reinforcement learning literature as independent DQN, which does not have strong guarantee of convergence to global optimal policy, especially in complex environment with multiple agents, where the number of agents can go to 10 or 20 agents or even more. However, empirical results in research often show IQN is still a very competitive performance, and it can be used as a strong benchmark for more complex smart algorithms. Ongoing work is to improve the current architecture using in order to achieve better convergence on more complex scenario settings. For example, high-dimensional state and action space with even sparser reward signal by using additional state-of-the-art more algorithms, for example, Q-mix or value decomposition algorithms, in order to combine coordinate the learnings of the individual agents. So this is the end of my presentation. Thank you so much for the opportunity and your attention to my presentation. I welcome all the questions you may have on our work.